Hello everyone, and welcome to the Week 13 review for Math 2414. In this one, we'll be continuing going over some of our tests for series, starting with the comparison tests. So we have two kinds of comparison test. The first one is fairly straightforward. It is the direct comparison test. And what this one says is it says if we have two series, the sum of a sub n and the sum of b sub n, and we know that a sub n is always smaller than or equal to b sub n, well then, if the sum of a sub n diverges, well then b sub n is larger, so the sum of b sub n would also have to diverge. On the other hand, if the sum of b sub n converges, well then the sum of a sub n has to converge as well. And if we wanted to just sketch out a picture for it, basically if we have that, well, 0, we're making both of these series positive, but basically if we have our a sub n and our b sub n, well, our b sub n is larger, well then if the sum of our b sub n converges, well then a sub n, which is smaller, has to be between 0 and that sum of b sub n, so it would also have to converge. And if a sub n diverged, well then it's going to push b sub n to infinity as well. So then b sub n would diverge as well. So let's see. Yeah. So let's do a quick example of how we could use this one. Let's say we have the sum of n equals 1 to infinity of n minus 4 over n cubed plus 9. Well, notice that n minus 4 is smaller than n, and n cubed plus 9 is larger than just n cubed. So if we divide by n cubed plus 9, that's going to get something smaller than just dividing by n cubed. So we actually have this inequality where the sum from 1 to infinity of n minus 4 over n cubed plus 9 is always smaller than the sum from 1 to infinity of n over n cubed. But this sum is equal to the sum from 1 to infinity of just 1 over n squared, which converges by few series. Then we can say by direct comparison test, which you'll often see abbreviated DCT, we have to have that the sum from n equals 1 to infinity of n minus 4 over n cubed plus 9 converges as well. Go ahead and try a quick practice problem. See if you can determine the convergence of the sum from n equals 2 to infinity of sine squared of n divided by n cubed minus 1. And I'll give you a couple minutes to work through that. All right, let's go over this problem. So for starters, we know that sine squared of n is always positive, and when n is larger than 2, so is n cubed minus 1. So we can actually write, because sine squared of n is always smaller than 1, this is smaller than or equal to the sum from n equals 2 to infinity of 1 over n cubed minus 1. Now, we can't just compare this directly to 1 over n cubed, because 1 over n cubed is actually smaller than 1 over n cubed minus 1. But what we can do is we can actually compare it to 1 over n squared, because we can say that n squared is smaller than n cubed minus 1 when n is larger than 2, which means that 1 over n squared would be greater than 1 over n cubed minus 1. Which means, since this series here converges, well then overall, by a direct comparison test, the sum from 1 to infinity of sine squared of n divided by n cubed minus 1 must converge as well. All right, moving on. The next comparison test is known as the limit comparison test. And the limit comparison test is my favorite comparison test, my favorite series test of them all, in fact. It is fantastic. And the idea behind the limit comparison test is it's really good at getting rid of a lot of like fluff in lower terms. So let's just start with the definition. Suppose we have the sum of a sub n and the sum of b sub n. Well, if we have that the limit as n goes to infinity of a sub n divided by b sub n equals to some number L, where L is not 0 and not infinity, well then, a sub n and the sum of b sub n share the same convergence. And when I say share the same convergence, what that means is they either both converge or they both diverge. So let's do an example. Suppose we have a really unpleasant looking series like the sum from 1 to infinity of n squared plus 2n minus 1 all over n to the 4th plus 3n cubed minus 2. Well, I'm going to define a second sum, and I'm going to make my b sub n just be equal to the largest term on top and the largest term on bottom. That simplifies to 1 over n squared. So my 1 over n squared then is my b sub n. So now if I take the limit as n approaches infinity of my a sub n, which is n squared plus 2n minus 1, all over n to the 4th plus 3n cubed minus 2n over my b sub n, which is 1 over n squared. This is the limit as n goes to infinity. I apply keep, change, flip, so I can rewrite my division of fractions as multiplication by the reciprocal. So now times n squared over 1, which is the reciprocal. This is the limit as n approaches infinity of n to the 4th plus 2n cubed minus n squared over n to the 4th plus 3n cubed minus 2n. And this limit is 1. The way we can find this limit is you can look at simply the largest term on top and bottom. On top it's an n to the 4th, on bottom it's an n to the 4th because it's balanced. The limit is going to be the coefficients. Another way you can think about it is if you divide everything by an n to the 4th, this becomes a 1. All of these other terms have n in the denominator, so they'll go to 0 as n goes to infinity. And then similarly, this becomes a 1, and these terms go to 0. 1 over 1 gets you 1. Which means because this number 1 is larger than 0 and smaller than infinity, we have that a sub n and b sub n share convergence. But we know that the sum from 1 to infinity of 1 over n squared converges by the p-series test. So then because of that, the sum from 1 to infinity of n squared plus 2n minus 1, that should be 1, over n to the 4th plus 3n cubed minus 2n should also converge, this time by the limit comparison test. Okay. Time for a practice problem. Go ahead and see if you can determine the convergence of the sum from 1 to infinity of 2n squared plus 3n over the square root of 5 plus n to the 7th. And I'll give you a few minutes to work through that. All right, let's go over this problem. So, again, I'm going to choose my b sub n by taking the largest term on top and the largest term on bottom. So my largest term on top is an n squared. my largest term on bottom is a square root of n to the 7th, which is n to the 7 halves. Canceling, I get 1 over n to the 3 halves. So if I apply my limit comparison test, I take the limit as n approaches infinity of 2n squared plus 3n over square root 5 plus n to the 7th divided by 1 over n to the 3 halves. Now division by fractions is the same as multiplying by the reciprocal, so I can just say times n to the 3 halves over 1, which is the limit as n approaches infinity of 2n to the 7 halves plus 3n to the 5 halves, all over the square root of 5 plus n to the 7th. And again, this limit gets me actually 2 this time. And how I can see that is I can divide everything by an n to the 7 halves. And this becomes 2. N to the 7 halves divided by n to the 7 halves is just 1. So plus 3 divided by n, that's n to the 5 halves divided by n to the 7 halves. We have square root of 5 over n to the 7, because the half part is incorporated in the square root, plus 1. And then letting n go to infinity, this term goes to 0, this term goes to 0, which is 2 over 1, which is just 2. So that's my limit. Now, because this limit 2 is between 0 and infinity, and is not 0 and is not infinity, what I have is that this series converges, is that this series and this series share the same convergence. Now what you'll note is that the sum from 1 to infinity of 1 over n to the 3 halves converges, again by p series. So we have that the sum from 1 to infinity of 2n squared plus 3n divided by square root 5 plus n to the 7th converges by limit comparison. All right, so those are your 2 comparison tests. They're both a lot of fun, super enjoyable. Direct comparison is really nice. Limit comparison is a blast. Both very useful tests. Next, let's talk about a specific kind of series that's very special. This is called an alternating series. So what is an alternating series? An alternating series is, simply put, a series whose terms switch between positive and negative. They alternate between positive and negative, so that's where we get the name alternating series. And one thing that could look like is like 1 minus 1/2 plus 1/3 minus 1/4, and so on. Now, the thing about alternating series is that some terms are going to cancel each other out. Like in this one, we have 1 minus 1/2. That gets us positive 1/2. But the thing is, the terms canceled each other out, which means that a series that formerly was all positive and just built on itself could now have some cancellations. And what this results in is some series whose absolute value might diverge might have enough cancellations occur so that the alternating version might converge. So let's take a quick look at what is called the alternating series test. So let's say we have a series and it's alternating. And the limit as n goes to infinity of that series is equal to 0, or of that sequence, sorry. And each term is smaller than the term that came before it, which can be written as terms are decreasing. Then we can actually say that the sum of a sub n is convergent. But we can actually say more than this. if our sum is convergent, and the absolute value of our sum is convergent, we say that the sum of a sub n converges absolutely. If instead we have that the sum of the absolute value of a sub n diverges, then we say that the sum of our series converges conditionally, and that condition being it has to be alternating. And if these properties up here aren't satisfied, then we know that our series will diverge. So let's do a quick example. Let's say we have the sum from 1 to infinity of negative 1 to the n times 1 over n. Well, I'm going to say that my a sub n is 1 over n. The other part just makes it alternating. So I can see that the limit as n goes to infinity of 1 over n is equal to 0. I can also see that my a sub n plus 1 is equal to 1 over n plus 1. And this is smaller than 1 over n, which is equal to my a sub n. And I can see that this is smaller if I simply cross multiply. I get that n is smaller than n plus 1. So 0 is less than 1, which is a true statement. So a sub n plus 1 is smaller than a sub n. So my terms are decreasing. Another common way you can show that terms are decreasing is by using the derivative. So if I said, well, the derivative of 1 over n is equal to the derivative of n to the negative 1, so minus 1 over n squared. N squared is always positive, so my overall derivative is negative. So it's decreasing. That's just another way you can show that it's decreasing. But regardless, I have that my series is alternating, the limit goes to 0, and my terms are decreasing. So I can say that the sum from 1 to infinity of negative 1 to the n times 1 over n converges. However, if I take the absolute value, that would get rid of this negative 1 to the n. This diverges by p-series. So I have to say that the sum from 1 to infinity of negative 1 to the n times 1 over n converges, but only conditionally. All right, time for a practice problem. Go ahead and determine the convergence of this series. And I'll give you a few minutes to work through that. All right, let's go over this problem. So first off, the cosine of n pi actually makes this series alternating. If we think about it, cosine of pi is -1, cosine of 2 pi is +1, cosine of 3 pi is -1, cosine of 4 pi is +1, and so on. So we actually get that this is just bouncing between -1 and +1, which means that the rest of it is really the part that we care about. First off, we can see that the limit as n approaches infinity of the square root of n divided by 2n plus 3, well, the square root of n is a smaller term than 2n, so this is in fact going to go to 0. Next, we can actually see that, well, our terms do in fact get smaller. There are a couple of ways to do this. First off, we could try the derivative. So if we took the derivative, well, that would be using the quotient rule. Square root of n over 2n plus 3, take the derivative, we get 2n plus 3 times 1 over 2 root n minus root n times 2, all over 2n plus 3 squared, which is equal to, here we have multiply the 2 root n through, and we have 2n divided by 2 root n is square root of n, 3 over 2 root n minus 2 root n, all over 2n plus 3 squared, which is equal to minus square root n plus 3 over 2 root n over 2n plus 3 squared. And my claim is that this is smaller than 0. And we can see that because the denominator is always positive, so we just need to show that the numerator is smaller than 0. And we can see this because square root of n is actually considerably larger than 3 over 2 root n. So if we just subtract it over, we get negative square root n is smaller than negative 3 over 2 root n. If we multiply by a positive or by -1, then we have square root n is now greater than 3 over 2 root n. And we have to do this because whenever we multiply by a negative, our sign flips, so we square both sides, we get n is bigger than 9 over 4n. So then multiplying both sides by 4n, we get that 4n squared is larger than 9, and this is of course true for n larger than, about 2. So we get that after a certain point, all of our terms are decreasing because our derivative is smaller than 0. And this, of course, satisfies the second portion of our alternating series test. So we have that the terms go to 0 and the terms are decreasing. Then we can say by the alternating series test, we have that the sum from 1 to infinity of cosine of n pi times square root of n divided by 2n plus 3 would converge. But we have to say whether or not it converges conditionally or absolutely. So you can actually notice that the square root of n divided by 2n plus 3 is actually larger than 1 divided by 3n, because 1 square root of n is bigger than 1, and then 3n is larger than 2n plus 3, so 1 over 2n plus 3 is going to be smaller than 1 over 3n, which means we have this inequality, but this series actually diverges by p-series. So then this sum, which is the absolute value of our original series, would diverge. So we have that the absolute value of cosine n pi times root n over 2n plus 3 diverges. Then we have that our overall series would converge conditionally because the alternating form converges, but the absolute value diverges. All right. Cool. So let's move on. We have, so for some other series, especially with the integral test, use the integral test to approximate the remainder of a series sum after n terms. So we have a similar theorem for the remainder of an alternating series. And the theorem says that if we have an alternating series and it is convergent, absolutely or conditionally, it doesn't matter. Well, then what we have is we have the remainder after n terms is going to be smaller than less than or equal to the next term. So in other words, the overall remainder is always less than or equal to just the next term that's coming. So let's do an example. If we have the sum from 1 to infinity of -1 to the n plus 1 times 1 over n to the 6, and we want to make our remainder after some number of terms smaller than 0.00005. Now the question we need to ask is how many terms are needed? How many terms are needed to make sure that our remainder is smaller than this number? Okay. So all we do is we need to figure out where this value here is going to be, so where our 0.00005, we just need to figure out where this is larger than 1 over n to the 6th. So if we actually plug this into a calculator, we get that they are equal when n is about equal to 5.21, which means that at n is equal to 5.21, then we get 1 over n to the 6th is 0.00005. Now, rounding up, we get that n equal to 6, so the 6th term is smaller than the error. Which means that because the 6th term is smaller than the error, our overall error would have to, is smaller than the error we want, well then the size of the 6th term would have to be smaller than our 0.00005, which means that the overall error would then be smaller than that. So our remaining error would have to be smaller than our 6th term, which is smaller than 0.00005, which means we need 5 terms, because after that, the error still remains within our desired bounds. So basically, we found this value. We said that after, when we round it up, we get that the 6th term would have to be smaller than our desired error, so the overall error would have to be smaller than that, which means we only need 5 terms. Time for some quick practice. Go ahead and find the number of terms needed to make the error of the series -1 to the n1 over n squared smaller than 0.001. I'll give you a few minutes to work through that. All right, let's go over this problem really quick. So if our remainder has to be smaller than 0.001, we know that 0.001 should be larger than our next term, which means that n is equal to, or sorry, 1 over n squared is equal to 0.001 when n is about equal to 31.623, which means that our 32nd term is smaller than our error, which then means that all of our other terms coming after that are smaller than our error, so we only need 31 terms to make sure that we have our error within that correct. Sorry, excuse me, boundary. So let's talk about a couple of other tests. Next up is the ratio test. This one is my second favorite test after the limit comparison test. So let's just start with what the ratio test says. So if we have the sum of some series a sub n, or the sum of some sequence a sub n, then we take the limit as n approaches infinity of a sub n plus 1 over a sub n. And we take the absolute value of that. We would get some number L out. And depending on the value of this L, we can say something about the value of our series, or about convergence of our series. So if L is smaller than 1, then we can actually say that our series converges. If L is larger than 1, we can say that our series diverges. And if L is equal to 1, then the test is inconclusive. Okay. So let's do a quick example of the ratio test. Suppose we have the sum from 1 to infinity of n factorial divided by n to the n. Well, we need to take the limit as n goes to infinity of a sub n plus 1 divided by a sub n. Of course, we would want to take the absolute value of that. In this case, everything's all positive, so it doesn't matter a ton, but it's a good form to put those absolute value forms. So a sub n plus 1 would be n plus 1 factorial divided by n plus 1 to the n plus 1, all over n factorial over n to the n. Again, I'm going to rewrite my dividing by a fraction as multiplying by the reciprocal. So now I have n plus 1 factorial divided by n plus 1 to the n plus 1 times n to the nth over n factorial. Now, one of my properties of factorials is I can write my n plus 1 factorial, that's n plus 1 times n minus 1, all the way down to 1. So I can actually write it as n plus 1 times n factorial. Similarly, I'm just going to pull out a single n plus 1 from this, so it's n plus 1 times n plus 1 to the n. And then I still have multiplied by my n to the n over n factorial. Now, a couple of things are going to cancel. First off, my n factorials cancel. And I also have an n plus 1 that cancels. So what I'm left with is the limit as n approaches infinity of n to the nth divided by n plus 1 to the nth, which is the same thing as the limit as n goes to infinity of n divided by n plus 1, all of this to the nth, which is the same thing as the limit as n goes to infinity of n plus 1 divided by n to the negative n, which is the same as the limit as n approaches infinity of n plus 1 over n. I'm going to break that up. So n over n plus 1 over n is 1 plus 1 over n. Then all of this is to the n and to the minus first power. Now, 1 plus 1 over n to the n, taking the limit as n goes to infinity, that is actually a special limit. That comes out to e, and of course we still have this exponent of negative 1. This is 1 over e, which is smaller than 1. Now, because this 1 over e value is smaller than 1, we can say that our series will converge. And it converges by the ratio test. Cool, cool. So the ratio test is particularly useful when you have things like factorials and exponents. It will actually show you that all your geometric series with a ratio smaller than 1 will converge. And overall, it's just a pretty great test. Next up, we have the root test, which is really similar to the ratio test. So what the root test is it says if we have the sum of some sequence a sub n, then we take the limit as n approaches infinity of the nth root of that sequence, specifically the absolute value of that sequence, and we'll get some number L out. And the rules are actually the exact same. If L is smaller than 1, then our series is actually absolutely convergent. If our L is larger than 1, then our series is divergent. And if our L is equal to 1, then it is inconclusive. All right. So time for, I think, a few practice problems. We'll end on these. I don't have an example for the root test, but I could recommend it for perhaps a couple of these practice problems. So first off, all you're going to be doing is determining whether or not these series converge. First, we're going to have the sum from 1 to infinity of 3n plus 1 divided by 4n minus 4. Actually, we're going to make that to sum from 2 to infinity, so our first term isn't undefined. Second, we're going to have the sum from 1 to infinity of minus 9 to the n divided by n times 10 to the n. And finally, we're going to have, actually going to move this one down a bit, give ourselves a bit more space, the sum from 1 to infinity of n factorial divided by 100 to the n. I'll give you a few minutes to work through those. Good luck. All right, let's go over these problems. So first off, the first one we can use either the ratio test or the root test. In this case though, I think that the root test is going to be a little bit better because when we take the limit as n goes to infinity of the nth root of 3n plus 1 over 4n minus 4 to the n, our nth root and our nth power actually cancel, and we're left with the limit as n goes to infinity of 3n plus 1 over 4n minus 4. Now, this limit, again, we can just look at the coefficients, or at the largest term on top and the largest term on bottom. We have a 3n on top and a 4n on bottom, so our limit is 3/4. Now, this is smaller than 1, so we have that our series must converge by the root test. All right, the second one, we have a couple of options. We could use the root test, we could use the ratio test, we could even, if we so desired, use the alternating series test, although if we use the alternating series test, we'd probably end up needing another test if it converged to show whether it converges conditionally or absolutely. So I'm going to start off with the ratio test. So I'm going to take the limit as n approaches infinity of the absolute value of -9 to the n plus 1 divided by n plus 1 times 10 to the n plus 1. And instead of dividing by the original, I'm just going to go ahead and multiply by the reciprocal. Oh, that was interesting. So multiplied by n times 10 to the n divided by -9 to the n. Now canceling whatever I can, I see that this is the limit as n approaches infinity of, I'm going to go ahead and ignore all my negatives and just drop my absolute value. So now I have 9 times 9 to the n times n times 10 to the n divided by n plus 1 times 10 times 10 to the n times 9 to the n. Now I can cancel my 9 to the n, and cancel my 10 to the n, and I'm left with the limit as n approaches infinity of 9n over 10n plus 10. And again, this is a balanced rational equation, so I take the largest term on top, 9n, and the largest term on bottom, 10n, and I get that this is 9/10, which is smaller than 1, so it converges by the ratio test. If I wanted to work this out using the root test, well, then I would take the limit as n approaches infinity of the nth root of the absolute value of -9 to the n over n times 10 to the n, which is the limit as n approaches infinity, the nth root of n times 9/10 to the n, which is the limit as n approaches infinity of 9/10 times the nth root of n. And of course, the nth root of n is simply, apologies. What was I thinking? oh dear, the nth root of n actually approaches 1, as n approaches infinity. So this limit is 9 over 10, which is again smaller than 1, so this one converges. The nth root of n does take a bit of thought to reason through why that would be 1. So in this case, the ratio test might be a little bit better just because it gives you a more clear step-by-step process. So yeah. All right, so that's 2 different ways to solve the problem, one using the ratio test, one using the root test. And in both cases, we see that it actually converges absolutely. So we don't even need the fact that it converges or that it's alternating, because if it converges absolutely, then the alternating version will naturally be convergent as well. All right, this final one, I would recommend using the ratio test. Some of you might have seen this n in the exponent and thought, ooh, I could use the root test, but the ratio test tends to work really well with factorials, whereas the root test tends to struggle with factorials. So let's apply the ratio test. We'll take the limit as n approaches infinity. Again, I'm going to say it's a sub n plus 1 multiplied by the reciprocal of a sub n. So this is n plus 1 factorial over 100 to the n plus 1, and I'm just going to multiply by the reciprocal, so 100 to the n over n factorial, which is the limit as n approaches infinity of n plus 1 times n factorial divided by 100 times 100 to the n times 100 to the n over n factorial. And I can cancel my n factorials, I can cancel my 100 to the n's. And what I see is that I actually have the limit as n goes to infinity of n plus 1 over 100, which is of course infinity. Now infinity is larger than 1, so this one actually diverges by the ratio test. All right, so that is all that I have for you today. Thanks for coming in and have a great, great day.